Most people think of a model as one monolithic thing that runs. It's not. Every model you have ever used, GPT, Claude, Gemini, has gone through two completely distinct phases, and they could not be more different. Here's the shape of it. Training, which is on the left hand side, costs you $100 million. It takes months, it takes thousands of CPUs, it does billions of weight updates. Inference, which is on the right side, costs you half a cent. It replies back in milliseconds. It takes only one forward pass. Weights are frozen. There is no learning at all. Same model, two completely different worlds. Every time you open Claude or ChatGPT, you are living on the right hand side of the diagram. The left side already happened. Someone else paid for it. Let me show you exactly what each side involves. Look at this diagram. 5 nodes, 1 cycle. This is training, stripped to its skeleton. It starts at data, trillions of tokens. Every book, every web page, and every single piece of code that lab could get their hands on. That data flows into forward bus, the model that makes a prediction on what comes next. It guesses, probably wrong at the start. That prediction flows right to loss function. How wrong was it? The loss function puts a number on the error. The number flows down to backpropagation. This is the expensive part. Trace the error back through every single layer of the network, computing how much each parameter contributed being wrong. That flows left to the weight update, which nudges every single dial, slightly less wrong than before. Then the dashed green line at the left, repeat. That cycle, data, forward, loss, backdrop, update, repeat, runs hundreds of billions of times. Each pass slightly better. Each pass costs compute. Multiply by hundreds of billions and you'll start to understand the bill. Let me put a real number on it. 10,000 H100 GPUs. Each chip cost about $30,000 to buy. You need them running for weeks. The training bill for a frontier model, GPT-5 class, Gemini class, Claude class, is somewhere between 50 and $200 million. And that includes the failed runs as well, because the runs tend to fail. The third car, that's a silent killer. In training, you don't just store weights, you store gradients for every single parameter. You store optimized states, the history that learning algorithm needs. That's 3 to 10 times more memory than just running the model. Here's the thing that should liberate you. And you'll almost certainly never train a fraudulent model, and that's not the ceiling, that's the deal. Someone else absorbs this cost, you rent the result. But to rent it intelligently, you need to see what the results look like. Look at this. Every cell you are seeing, that's a parameter, a weight, a number. And every time it flashes, that's the update step firing, nudging that particular dial. What's the last number? It's dropping. 2.7, 2.6, 2.5, and the iteration counter. 1 million, 2 million, 5 million, 10 million. Each one of this is one pass through the training cycle we just saw. This is what training looks like from the inside. Not glamorous, not dramatic, just an enormous number of tiny corrections happening very fast for a very, very long time. This runs until someone decides enough, the model is ready. And then it stops, frozen. Every dial locked, no more updates, no more learning, that's it. Here's the thing most people don't realize. The model is not learning from your conversation. Every time you open a chat with Claude, the model has the same weights it was trained on months ago. Your prompts don't change it. Your correlations doesn't change it. The model you talk to today is the model they finished training last year. That's not a bug, that's the design. If the model updated from every conversation, it would be unstable. It would forget what it learned, drift in unpredictable directions. The freeze is what makes deployment possible. Now we get to inference, the phase you live in. You send a prompt, it gets tokenized, broken into chunks, the model understands. Those tokens becomes number and get pushed through every frozen networks, layer by layer. What's the layers lighting up? Layer 1, layer 16, layer 32, all the way up to layer 96. One forward pass, input flows in, output flows out. And here's what's not happening. There is no backward pass. There is no gradient stored. That's the whole difference. In training, forward and backward pass cost you like enormous amount of memory. In inference, it is forward only. And that's why it costs you minimal memory. And notice the loop. The animation restarts because that's what is happening. Every time you read a response streaming in word by word, one forward pass per token, same frozen bytes, same architecture, just different input each time. The repetition is cheap. Each pass costs you a millisecond. Each pass costs you a fraction of cent. Hundreds of millions of users doing this simultaneously, and the model doesn't update once. Let me put up a gap in a table so it sticks. Training takes you months, inference takes in milliseconds. Training needs weight plus gradients plus optimizer states. Inference doesn't need anything. It just requires weights. Training has backward pass. Inference doesn't need it. Training of frontier models, 50 to $200 million. One conversation with Claude API, 3 tenths of a cent. Three things that create a gap. First, no gradients in the memory. Inference is a single lookup through frozen values. Training is a lookup and write back through every layer. Second, parallelism flips. In training, you parallelize over batch size to fill in GP memory. In inference, parallelizes over uses. Many people, one model, fraction of a cent each. Third, inference hardware is converging. Companies like Croc are building chips designed purely for forward passes. No computation based on backward passes that aren't happening. The hardware bridge is narrowing fast.